All right, in this last example, we're going to evaluate the Riemann sum for this function f. And we're going to use sample points. Our sample points are going to be the right endpoints. And we're going to use 6 subintervals in our work. So here's our function, x cubed minus 6x. We're looking at the interval from 0 to 3. And so we're going to evaluate the Riemann sum for this function on this interval. So there's a lot of things that are specified here. We have a function, we have an interval, and then we also are told we're going to use right endpoints and 6 subintervals. All right, so the first thing we want to do is get the width for each of our subintervals. So this was delta x. And in general, it's b minus a over n. So a and b are the endpoints from our big interval from, in this case, 0 to 3. So it'll be 3 minus 0, and then n is 6. So 3 over 6 is 1/2. And a lot of times it's helpful to use decimals here. So we'll think of this as 0.5. All right, so what we're doing is we're looking at this interval from 0 to 3, and we're going to slice this up into 6 subintervals. And so next we want to find the right endpoints. So that's what we're going to find next. And so let's kind of think of our number line here. We're looking at from 0 to 3. And what we're going to do is we're going to slice this up into 6 smaller pieces. Nope. Like that, I think. Let me see. 1, 2, 3, 4, 5, 6. Yes. All right, so we've sliced it up into 6 subintervals. And what we want to do is we're going to use the right endpoints. So for instance, this first subinterval here, here's our first subinterval. We're going to use the right endpoint on that subinterval. So that's going to be our first right endpoint. So we call that x1 star. And so the way we calculate x1 star, our first sample point, is it's just a plus delta x. So if we look at this subinterval, it's just our starting value, which starts at 0, and then we just go a full width, so full delta x here, and that's going to be our first sample point. So in general, it's a plus delta x, but for this specific problem, our a value is 0, and we found delta x to be 0.5. So our first sample point is going to be at 0.5. And then we repeat this. We're going to get x2 star, x3 star, 4, 5, and 6. And the way we find these, once we have the first one, the way we find the rest of them is we just add in delta x. So to go from x1 to x2, add delta x. So we're at 0.5. If we add another 0.5, it's going to be 1. Now to go from x2 to x3, what do? We add delta x again. So we're at 1. Our delta x value is 0.5. So we're going to be at 1.5 here. And then we keep going. So we're at 1.5. Now we're going to add another delta x. This will give us x4. So we'll go up to 2. and then we'll be at 2.5, and then we'll be at 3 if we just keep adding delta x. So 2 to 2.5 plus delta x. 2.5 to 3 plus delta x. So once you have the first one, once you have x1, then you just kind of keep repeating, add delta x, and it gets you the rest of them. Now graphically, if we were to look at what we're doing, say on the graph of our function here, what we're doing is we're looking at the kind of the section of our x-axis going from 0 to 3. And what we've done effectively here is we're going to slice it up into 6 smaller pieces, and this just tells us which point we're going to use to get the height of our rectangle. And so our first rectangle, what this is saying, is going to happen at 0.5. So we find 0.5 on our x-axis, and we go until we figure out or see the corresponding point on our curve, which is right there, and we form an approximating rectangle. So we're using x1, that's telling us the x location for our first rectangle. Then for our second rectangle, the location is going to be at 1. So we go find x equals 1 on the graph here, find the corresponding point, and then we form a second approximating rectangle. And we just keep doing this until we have 6 rectangles here. So the next location, our third rectangle, is going to happen at 1.5. So we find 1.5 along the x-axis, find the corresponding point on our curve, and then form a approximating rectangle there. And then, so we have 3 rectangles now. Now we want our fourth one, which is going to happen at x equals 2. So we find 2 along our x-axis, figure out the corresponding point on our graph, and then use that to give us a rectangle. And then 2.5, find 2.5 along the x-axis, and there it looks like maybe find the corresponding point on our curve. So there it looks like we might be a little bit above. And then finally for our 6th rectangle, so now we have so far we have 5 rectangles drawn in. For our 6th one, we're going to use the location 3. So we find 3 along our x-axis, and then we just read up and find the corresponding point on our graph. So I'd say somewhere around there. And that's going to give us the height for our last rectangle. All right, so these sample points, these right endpoints, they're kind of telling us where to draw in our approximating rectangles. All right, so now this is kind of the setup here. Now let's actually do the calculation. All right, so there are the approximating rectangles that we just drew in. And what we want to do is evaluate the Riemann sum. So the Riemann sum is actually the sum from I equals 1 to 6 of f of xi star times delta x. All right, just for the practice, let's practice writing this out. So x1 star, what did we find for x1 star? That was 0.5. So this will be f of 0.5 times delta x. Then what was what was x2? That was 1. So we're going to plug 1 into our function times delta x. And we keep repeating this. So this is x2. And as you do this, you might notice that we can actually, each of these terms here is going to have a delta x in it. And delta x isn't changing. So we could actually, to kind of simplify this a little bit, we can actually factor delta x out. And why that's helpful is it just produces less multiplication then. So, there's going to be more terms here. So there'd be, f of x3 times delta x, f of x4 times delta x. All of them are going to have a delta x. So let's actually factor these delta x's out. So if you're writing this down, just kind of cross this out. And what we're going to do instead is just to simplify this. What we're going to do is kind of write out all of our function values added together. And then we factor out delta x. So it's all going to be times delta x here. So that can be helpful just to, so you're not writing as much with these Riemann sum calculations. So, this is x2. This value is what we found for x3. This is what we found for x4, x5, and x6 right here. And that was because we were doing the right endpoints. All right, so we have our Riemann sum all written out. We've kind of done a little bit of arithmetic here, a little bit of algebra. We factored out the delta x just to make things a little bit not as much writing. And then to get these function values, we're going to take the x value and plug it in right here into our function. So we actually have a formula for our function here. The graph can be helpful, but we actually have the graph, or we actually have the formula here. So take 0.5, and if we plug it into x cubed minus 6x, what we end up with is negative 2.875. Now it's negative because, well, you can see the curve is below the horizontal axis. And then we just play the same game for all these other ones. So when I plug 1 into this function, I get 1 minus 6 is negative 5. When I plug 1.5 in, what do I get? I get negative 5.625. And then if I plug 2 in, I get 8 minus 12, I get negative 4. And 2.5, what do we get? We get plus 0.625. And that's this one right here where the function, where we can see the approximating rectangle is now above the horizontal. And then we take the last x value 3, plug it in, we get 27 minus 18, so we get plus 9. And then this is all times delta x, and delta x here is the width of each of these rectangles, and they all have the same width, and we calculated that to be 0.5. All right. So if we add all this together, what we end up with is negative 3.9375. And a lot of times the way we denote this numerical value for a Riemann sum is we use a capital R if we're using right endpoints, and with a little subscript of 6. So the R here is telling us we used right endpoints, and the 6 is telling us the n value. So if we use left endpoints, we would say L6, or if we use midpoints, we would say M6. So that's sometimes a little shorthand notation to represent the Riemann sum using right endpoints with n equal to 6. All right. And what we get here, this negative 3.9375, what we're seeing is these rectangles that are below the horizontal axis are contributing a negative value, and these rectangles that are above the horizontal axis are contributing positive values. So a way to interpret this, if we're thinking of these Riemann sums and definite integrals in terms of area, what we're seeing here is adding up these negative terms times delta x would give us an approximation for the area under the curve if we adjust for the negative. And then adding up those positive terms would be like adding up and then multiplying by delta x would give us the area for these two rectangles that are above. So the negative terms here, the reason why they're negative is because they're below the horizontal axis. And these positive terms are positive because they're above the horizontal axis. And, you know, in this example, we're using n equals 6. You know, that's fine. But normally we try to do Riemann sums. Actually, in practice, we try to do these so that n is relatively large. We're using a large number of rectangles here. And so how that might look is something like this. We have the graph of our function, and here we see it with 25 rectangles plotted, right endpoint rectangles. And you can see already this is a much better representation for our region compared to what we did with just 6. 6 did an okay job kind of giving us an idea of our region. But if we up it to 25, we have a much better representation. And so the idea with the definite integral is we have these Riemann sums that we can do. The sum from I equals 1 to n of f of xi star times delta x. And the idea is that if we let n increase, let n go to infinity, what happens is these rectangles get very thin, and we get a very nice representation for our region under the graph, and that's our definite integral. So doing the limit as n goes to infinity of our Riemann sum, our Riemann sums, that gives us our definite integral. And what we can think of is, looking at this, the value of our Riemann sum is, another way to think of it in terms of area, is it's the area of the rectangles that are above minus the area of the rectangles that are below. So these rectangles here that are above, we can figure out their area. All these rectangles that are below, we can figure out their area. And when we calculate the Riemann sum, what happens is those rectangles that are below, those are giving us, when we do the Riemann sum, those are giving us a negative value. And so we get the area for these rectangles that are below, above. When we kind of add everything together, we get the area for these rectangles that are above minus the area for these rectangles that are below. And that's precisely what we are seeing in this. These first 4 negative values times delta x were giving us, in some way, the area for these 4 rectangles, but they're giving us a directed area. They're telling us we know what the area for these rectangles are, but the value is going to be negative because it's below the horizontal axis. Whereas with these 2 rectangles, we got positive values. So the area for these rectangles are going to be positive. And so the Riemann sum, if we kind of put everything together, all the rectangles that are above, we can figure out their area for. All the rectangles that are below, we can figure out the area for. And so what ends up happening is we get the area for the above rectangles minus the area for the below rectangles. And if we're going to calculate the definite integral here, what it's doing is it's giving us the area for this region that's above minus the area for this region that's below. And we also called this the net area. So that's what we're getting with this definite integral here. It's the area for this above region minus the area for this below region. All right, so that's going to do it for our discussion of the limit definition of definite integrals, really involving Riemann sums. All right, we'll see you later. Bye-bye.